Hello, everybody. Thanks for coming. I'd like to take the next few minutes here to build on the earlier presentation and give you a sense of the engineering work that went into the development and implementation of this novel composite bridge girder that you heard Ken speak about a few moments before. The hybrid composite concrete bridge is shown here schematically. And development drivers and its key features are its lightweight, the fact it's easily transportable, it's corrosion free and highly durable therefore, but it's just a girder bridge at the end of the day, and it's built in the same way we would build a girder bridge, having steel girders or concrete girders. A little bit of background and timeline here, and we'll talk, this will also serve as an outline for this presentation. The girder was originally developed by Maine with funding from the U.S. Army Engineering Research and Development Center. That goes back to 2015. So there was a 3 or 4 year development process from conception to proof of concept. And that proof of concept really was accomplished with the bend testing of a 40-foot long girder that we completed in 2018, a little over 3 years ago. But that also necessitated much more extensive development and improvement of critical components like girder deck shear connectors. As you just heard, AIT Bridges designed a 75-foot span bridge on US Route 1A in Hamden, the Gristmill Bridge. Construction of that was completed in December of 2020. And prior to the bridge being open to traffic on New Year's, actually, the UMaine instrumented and live load tested that bridge in partnership with UMass Lowell to give us a baseline performance data on that structure and prove that it behaves as expected in the real world. And we'll talk about all of these things. Starting with that 40-foot test girder, here's a cross-section of what that original prototype girder that we tested in the lab looked like. And it has the same characteristics as the girders that are used today. It's a tub girder section. It's got solid E-glass FRP top flanges. It's got foam core webs with E-glass FRP waste web face sheets. Those are plus minus 45 layers to carry shear. And it's got carbon fiber in the bottom flange to give us extra tensile reinforcement, stiffness, and strength. And it's made composite with the concrete deck through mechanical shear connectors. And the ones that were used in that 40-foot test girder cross section we'll call the first generation shear connectors. And as you might be able to tell from the photo, they're actually pretty complicated, and it turns out not very good, as we'll see. And this girder also had a precast concrete deck. It was a panelized precast deck with grout channels that were filled after the deck panels were placed on the girder. Here's a picture of that 40-foot test girder immediately following its infusion in our lab at the University of Maine. It was infused in a large 3D printed mold, which was itself a pretty novel part at the time. If you look closely, you can see some PEX pipe running there. It was actually water cooled because of the exothermic reaction of the resin. We weren't sure if that was necessary or not, but it seemed like a good idea when we first did it as a belt and suspenders approach. And standard vacuum infusion, but a large part and a complicated part. The fiber architecture is such that it's not trivial to lay one of these up. And a lot of improvements have been made in manufacturing since this first girder to alleviate some of those issues. Here's the test setup of that girder in the 4-point bending rig at the University of Maine. You can see the spreader beam and applied load coming down from a frame, and that spreads the load out to 2 load points to create the 4-point bend test, so a region of constant moment around mid-span, and then constant shear and linearly varying moments at the ends. Large diaphragms were cast at the ends to mimic how the girder would actually be fabricated in the field, and those precast deck panels here are already in place and have been grouted together. Now, what we got out of this were some really interesting results and very positive. This is a plot of load versus midspan deflection from that test. And there are 3 load displacement plots on there, a couple going to lower loads, the blue line and the red line, and then that orangish line we drove the girder to failure at about 377,000 pounds. To put that in perspective, that's 2.65 times the AASHTO factored load with what's known as the Maine modified design truck, which is an HL93 truck with its weight increased by 25%. That's a very large load. That implies a massive factor of safety. That's not accidental. In fact, if you look at the design of that girder and you account for all the strength reduction factors that must be applied and then the load factors and everything else, that 2.65 is almost exactly what we would have predicted it to be. And another line here is the dashed purple line, and you can see that that represents the factored loading, not the service load, but the factored loading, which is a massive load, and we've got a lot of reserve capacity in there. Now, the shear connectors are an incredibly important part of this and a big reason why it works. And that girder exhibited essentially fully composite action between the girder and the deck during the test. Good strength performance, but we know from experience with steel girders that fatigue usually governs shear connector design. And we had to assess that. That drove us into another phase of this work where we took a really close look at the shear connectors. And so we constructed a fatigue test, a simple test where we have a concrete block, a couple of FRP plates that are the same as the top flanges of the girder, and then we embed those shear connectors when we cast the deck. We bolt those flanges on there, and then we apply cyclic loads via compression. We put that concrete block on the floor, we apply the load to those girder top flanges, and we put those shear connectors in shear, just like they are in the real girder. And what we found is that those first generation studs that were used in that 40-foot girder, well, they had plenty of strength, but they did not have enough fatigue capacity. They failed at, in some cases, less than 1 million fatigue cycles. And what they needed to carry, based on the same criteria that we use for steel girder bridges, they needed to carry about 6 million cycles. So that drove us to the second generation of shear connector. We got the threads out of the shear plane, moved away from threaded rods. This is steel design 101, right? Get a plain shank in the shear plane. A490 bolts, which have better material properties, better fatigue resistance, and these very comfortably carried 6 million cycles of factored fatigue load. And they met AASHTO's criteria, and you can see a before and after picture here with a connector, and very little damage to the FRP, negligible loss in stiffness as well. So this gave us really good confidence in this technology. But we wanted to take it a step further, and we did. We continued this work, and we thought, well, you know, it needs a lot of bolts. They're about every 6 inches on center. If we can create a deformed surface on the top flange of that girder and then cast the deck against that or grout against that deformed surface, we can create a mechanical shear connection where the bolts don't really have to do anything. And that led us to this third generation connector. You see a top flange plate on the left with the corrugations that are infused into it during fabrication, concrete block cast against it on the right. And that is great because it results in, without going into detail, much simpler fabrication. We don't need tightly toleranced holes for those shear connectors. We can cut the number of shear connectors about in half. And we can now use like stainless steel threaded rod. And stainless steel, of course, itself has poor fatigue resistance, but it's not actually doing the work anymore. It's that roughened surface that's doing the job, and the connectors just hold it together. So now we've moved to the point where you can actually have a completely corrosion-free structure because your shear connectors can't corrode either. Now the Gristmill Bridge in Hamden, Maine, you heard that discussed a bit a moment ago by Ken, 75-foot simple span on US Route 1A, constructed in late 2020. This had a cast-in-place concrete deck. It actually has the second generation of shear connectors. It doesn't have that corrugated top flange. And this is a real example of how closely the university and AIT work together, and really how this work was fast-tracked. We were just developing and proving out the corrugated shear connectors when the Gristmill Bridge was being designed. And of course AIT has to take responsibility for that design. They're stamping those drawings, and so they've got to put their name on what's been proven, not what we think is going to work. So we weren't able to use those corrugated flanges on these girders. And AIT, of course, designed that superstructure. They fabricated those girders, 5-girder bridge, complex geometry that necessitated that cast-in-place deck. Maine was involved in that design, however, through the Region 1 TIDC Center. We performed some finite element analyses to assess girder stability, lateral torsional buckling in particular. You can see down here on the lower left. That's a limit state you got to check during construction, during the deck pour. Was not a problem. Top flanges were braced, but still we had to dot the I's and cross the T's. We ran some analyses to give an assessment of lateral impact forces on the girders. We documented the construction process and lessons learned there. And frankly, there weren't too many lessons learned, because once you successfully fabricate the girders, again, these bridges go together in a very straightforward manner. We then instrumented and load tested that completed bridge. And I'd like to talk for a moment about that. The construction of the Gristmill Bridge shown, we've got the cross section of the bridge shown here. This is in AIT's facility, and that gives you a good sense of perspective on the size of that girder. It shows that foam core web. If you look down at the bottom, you can see the carbon fiber in the bottom flange, the darker material, shear connectors there going through that solid top flange. And here's a nice picture from below with all 5 girders in place, and utilities are hung off there, water pipe, sewer pipe, and again, going together just like any other girder bridge. Now, the field load testing of the Gristmill Bridge, this was a great opportunity to get baseline data on this structure and assess its performance under large service loads. We installed 23 strain sensors at a variety of locations on that bridge. We put very heavy trucks at predefined locations, worked closely with the Maine DOT. We spec'd those trucks, so they were a great partner in this, because they're willing to make changes, do things like take plow frames off in the middle of winter to get the axle weights what we would like, and that was important. We recorded flexural strains under different loading conditions. We ran 4 different configurations of loading, and we compare those measured strains with expected values. There are always logistical challenges: installing the gauges over water, producing large loads, traffic control. Although traffic control here, not too much of an issue because the bridge was closed for us, right? But we've tested 30 some odd bridges over the last 8 or 10 years, and we hit all of these things with most of them. The load application is great bird's eye view here from a drone. So we had 3 axle dump trucks on there. They were overloaded, about 65,000 pounds per truck. So we put over 260,000 pounds on this bridge at once with the load case shown here. Distribution shown there: 17,000 pound front axle, a little heavier than normal because of plow frames, 24,000 pound rears. And that applied load, those 4 trucks, are approximately equal, almost exactly equal, to just a service HL93 live load with impact. So not even a factored load. And so that gives you a sense of how large our design loads are. They're massive. And notice we've got those trucks backed up to each other. So we have the 4 heaviest axles as close together as they possibly can be in both lanes. Our measured midspan strains under the 4 truck load, we instrumented all girders at midspan so we could get an assessment of load distribution. And we see the strains at the bottom of the girder are maximum positive, mid-depth of the web. The bottom of the girder top flange, they're still positive. The neutral axis, as expected, is actually up in the slab. Strains are varying nearly linearly through the depth of the girder. We've got all indications are really good composite action with that neutral axis up in the deck. The bridge is behaving very much like we expect it to, and the strains are pretty close to predicted values. Ongoing in future work here, we've developed some high fidelity 3D finite element models of the Gristmill Bridge and comparing measured and predicted behavior with those, and that work is progressing nicely. And is actually, we're just about ready to close that out, and the final report will be issued. And we've got other work going on in this area, looking at more refined values of web shear strength. Our current estimates for web shear strength that we use in design do appear to be conservative. We've done some pretty extensive experimental work to assess the true shear strength of those webs, and we'll be doing some buckling analyses of the webs to supplement the material testing, and also developing a guide specification for design, so to ease the design process and make it more transparent and easily applied by others and increase the market for these. We're also doing some large-scale testing of the double CT girder with a partial depth precast deck, and we've got a girder that is currently, we are getting ready to fail one, drive it to failure here, and within the next few days, and we're doing strength and creep testing of a 56-foot specimen as well, which we then expect to drive to failure. So that's going to give us more data on just raw girder flexural strength and shear strength that will further support this technology. So at this point, hopefully that gives you a better sense of the engineering and development that's gone into this. I'd like to thank you for listening and open the floor to any questions you may have.